from cross-datacenter KVCache offloading to the philosophy of whether AI can ever truly feel, and from formally verified explanations for safety-critical networks, today's episode spans the full spectrum of modern AI. We'll look at how hybrid attention models are reshaping infrastructure, why some researchers say simulation is not consciousness, and how formal methods can make neural network explanations more trustworthy. If you want a tour of where AI is headed technically and where its deepest boundaries may lie, stay with us. Let's explore the first paper. Prefill as a service KVCache of next-generation models could go cross-data center. Prefill as a service, PROFAS, argues that next-generation hybrid attention LLMs have lowered KVCache traffic enough to move prefills across data center boundaries, but only if routing and scheduling are made bandwidth aware. The paper's core claim is that reducing KVCache is necessary but insufficient. Naive full offload still collapses under bursty arrivals, skewed prompt lengths, uneven prefix cache locality, and variable intercluster bandwidth. PROFAS therefore offloads only long uncached prefills to dedicated compute-dense prefill clusters, then ships the resulting KVCache over commodity Ethernet to local PD clusters for decode, avoiding the need for a shared RDMA fabric. The key technical enabler is hybrid attention, exemplified by Kimi, Linear, MIMO, V2, Flash, Quinn, 3, 5, 3, 9, 7, B, and Ring 2, 5, 1, T, where linear or sliding window layers dominate and only a small fraction of full attention layers emit sequence length dependent KVCache. The paper quantifies the effect via KV throughput. FICV equals SKV divided by T prefill. At 32K tokens, MIMO V2, Flash drops to 4.66 gigabits per second versus 59.93 gigabits per second for dense Minimax M2. 5A 13 times reduction, Quen 3, 5, 3, 9, 7, B reaches 8.25 gigabits per second versus 33.35 gigabits per second for dense Quen 3, 2, 3, 5, B, A 4 times reduction for Ring 2, 5, 1, T. The paper estimates roughly 36 times total KV memory savings from architecture plus layer ratio. PROFAS adds a hybrid prefix cache pool, length threshold routing, bandwidth-aware scheduling, and a dual timescale controller that re-optimizes the prefill decode ratio. In a case study on an internal 1T hybrid model with 32 H200 PRFAS GPUs and 64 H20 PD GPUs optimized at T equals 19 4K tokens, the system routes 49.6% of requests remotely, uses only 13 gigabits per second of a 100 gigabits per second Ethernet link, and achieves 3.24 ReQ. S throughput, 54% above homogeneous PD and 32% above naive heterogeneous PD, while cutting P90 TTFT by 64%. Let's explore the second paper, the abstraction fallacy, why AI can simulate but not instantiate consciousness. Alexander Lurchner argues that computational functionalism fails because it confuses a map with the territory. AI can simulate consciousness-like behavior, but cannot instantiate phenomenal experience. The paper's central claim is the abstraction fallacy, the idea that computation is not an intrinsic physical process, but a mapmaker-dependent description imposed on continuous physics. To count as computation, physical dynamics must be alphabetized into a finite symbol set by an active experiencing agent, which the paper calls the mapmaker. On this view, abstract states such as pain or red are not free-floating formal objects. They are constituted concepts extracted from lived experience by thermodynamically constrained organisms. Symbol manipulation in machines is therefore only vehicle causality, voltage transitions, matrix multiplies, token updates, whereas consciousness would require content causality, the intrinsic physical constitution of experience itself. The paper formalizes implementation with a commutative diagram mapping physical states PP onto abstract states AA via an external function F, then argues that this mapping cannot be internal to the machine without circularity. It rejects the fading qualia argument, the Chinese room intuition, and emergence-based defenses by claiming they all assume the conclusion that syntax can generate semantics. Even embodied AI is said to fail. Sensors and actuators merely transduce inputs and outputs, while the algorithmic core still operates on alphabetized symbols. So robotics closes referential grounding, but not phenomenality. The paper also uses the Shannon constraint and the Melody paradox to argue that any fixed physical process can be mapped to multiple incompatible computations, showing that computation is underdetermined by substrate. The novel conclusion is not biological exclusivity. Artificial consciousness is not impossible in principle, but only if a synthetic system instantiates the relevant physical dynamics directly. Scaling LLMs, GPUs, or humanoid robots, the author claims, will not produce sentience. It will produce more accurate non-sentient simulations. Let's explore the third paper, Towards Verified and Targeted Explanations Through Formal Methods. Towards Verified and Targeted Explanations Through Formal Methods introduces VitaX, a formal XAI framework for safety-critical neural networks that answers a narrower question than standard robustness verification. Not whether a model is robust to any perturbation, but whether it remains stable against a user-specified high-risk target class. The key novelty is targeted epsilon robustness, a certified semi-factual property stating that perturbing a selected feature subset A by at most epsilon cannot change the prediction from class Y to target class T. VitaX first ranks input features by target-specific gradient saliency, X, F, T, X, then uses binary search over prefixes of that ranking with star set reachability verification via NNV, reducing solver calls to O log n rather than VeraX's ON or brute force 2n search. Empirically, VitaX was evaluated on MNIST, GTSRB, MNIST letters, and TaxiNet using MLP, CNN, ResNet, and Inception models. On MNIST and GTSRB, it achieved the best formal method fidelity, 0.56 and 0.78 respectively, while keeping the smallest formal method cardinality, 121.47 and 30.57 features. Relative to adapted Lime and Anchor's baselines, fidelity improved by over 5-6 times on MNIST and 37% on GTSRB. Compared with VeraX, fidelity improved 3.5 times on MNIST and 7.8 times on GTSRB, while runtime dropped from 691s to 1189s on MNIST and from 1534s to 4723s on GTSRB. On larger models, VitaX remained practical, producing verified explanations in under 70 seconds using CP star. The method's main limitation is that its guarantees are local, target-specific, and solver-dependent, but it is the first framework to combine targeted class boundary analysis with formal semi-factual verification. That's a wrap on today's AI paper highlights. Thanks for watching.